Hello there, everybody. Welcome to the second lecture in the MCAT A series for organic chemistry, and this particular lecture series is revolving around aldehydes and ketones. So the first lecture dealt with some of the subjects that are not in the red boxes. We talked about the structure and properties of aldehydes, ketones. We discussed the nomenclature and how to name them, and we also discussed some enolate chemistry and how to control the different keto-enolate formations, whether you're dealing with kinetic or thermodynamic formation. So what I've highlighted in red here is what we really want to take a look at today, and that's going to be reactions. So the reactions that we are concerned with are primarily nucleophilic additions. So you can see in the list here that it states we have the acetyl hemiacetal formation, the imine and enamine formation, hydride reductions, and cyanohydrin additions. Now, outside of that is also oxidation of aldehydes. Ketones cannot be oxidized. They are already as oxidized as they're going to get. However, aldehydes can be upgraded in terms of their oxidation into carboxylic acids. So we'll take a brief look at that. And then finally, we will conclude with aldol condensations. The aldol condensations also involve nucleophilic attacks, but the attacks will be using enolates as our nucleophiles. So they're going to be a little bit separate in terms of the chemistry when we look at those in comparison to the other essential reactions where we're dealing with the nucleophilic additions. So let's go ahead and get started with this. I want to first cover the acetyl and hemiacetal. Now, I know I mentioned in previous lectures that this is not the only set of reactions that aldehydes and ketones can undergo. So do keep that in mind. We're picking out the most essential reactions, especially when you're studying for the MCAT, the ones that are going to be the most relevant in terms of biological activity or biochemistry pathways. So this is the general setup when you are getting ready to deal with the acetyl hemiacetal formation. So what we have here is a ketone. I'm going to be using acetone for most of the examples that we're going to be dealing with today. So you'll probably see this starting material over on the left coming up again and again as I'm using acetone. Now, if we take a look here, let me just bring up my pen. This is the starting material. So here's our ketone, and I'll label that with a K. The product over here, this is the acetyl. And then the hemiacetal we're actually going to see is partway through this reaction. What is required is a ketone or an aldehyde. You need some sort of alcohol that's going to act as a nucleophile. And then the acetyl hemiacetal reactions are run under acidic conditions. So what you should be doing right now is thinking back to that first video. What did we say when we expose aldehydes and ketones to any type of acidic condition? So I'll give you guys a second. I want you to think about it. What would be the most probable first step in this mechanism based on what we learned in the previous video? All right, so hopefully you had a chance to think about that. I'm going to draw in the electrons on this oxygen because it is the oxygen that is going to participate first by grabbing one of the acidic protons. And that's what we learned. We said that when we're under acidic conditions, we tend to what's called activate the carbonyl. And so these conditions are reversible throughout the entire reaction. So you're going to see the double-headed arrows. Now, that's not true for every reaction, but some of the aldehyde-ketone reactions are reversible, especially when they're under acidic conditions, because we can reprotonate some of these nucleophiles that come in and make them leave. Now, our ketone is going to become activated. So we now have an OH here, and we've got a positive charge associated with this oxygen. Now the oxygen would have one lone pair left instead of two because it went in to attack the acidic proton. So at this point, now that we have an activated carbonyl, and when we say activated, we're saying because the oxygen has a positive charge associated with it, it's going to take some of these electrons, and if you remember, that means that I've got a large partial positive down at this carbonyl right here. Right? Now I'm just going to remove that because we want the alcohol to come in here. So the alcohol is going to be a nucleophile. The oxygen, again, remember nucleophiles need some source of electrons. The oxygen is going to provide the source of electrons, and it will come in and attack the carbonyl as the bond is moving up to this oxygen. And again, keep in mind that carbon can never have 5 bonds at any given time, even as an intermediate. So it would not be appropriate for me to bring in this alcohol and then in a separate step move this double bond up to the oxygen, because I would briefly be showing a carbon that has 5 bonds, and that's violating the valence rules. It does not have any d orbitals, and so it cannot have access to more than 4 valence bonds at the most. So once I do that, I again will draw my double-headed arrows here. I'm going to end up with the OH here. So now I have my alcohol, and this gets a lone pair back from the double bond that was there. And then I also have OH. Now keep in mind that this alcohol came with the hydrogen attached. So this oxygen is now going to be positive when we're taking a look at this. Okay? So in this particular condition, we could do what's called a proton transfer. Now a proton transfer is going to be where this hydrogen associated with the alcohol, this one right here, is going to end up being moved to this alcohol right here. That's what's going to occur in the proton transfer. So considering we have acidic conditions, this proton could leave into solution as H+. In other words, it's catalyzed. We're just regenerating our catalyst. And what you'll be left with in the intermediate here for a moment is what's known as the hemiacetal. So let's take a look at that. Let's say that this hydrogen will leave and give the electrons back to the oxygen here in order to make it neutral. So what we're going to end up with, if we do that, is we will have an alcohol up top, and we will have the OCH3 at the bottom. So if you notice, this is really showing you that I have completed 1/2 of what needs to be found in my acetal. So take a look at that right there. The OCH3s match. The question now is, how do I turn that OH into an OCH3? All right. So this right here is known as a hemiacetal. Now, the term hemi meaning halfway or partial, and then acetal because that's our product. So right now I have a half acetal or a hemiacetal. That's what I'm working with. That's this structure right here. Hemiacetals involve an alcohol and an ether. So that ether portionality, again, right here, okay, is going to come from the alcohol that was originally substituted in that nucleophilic condition. Right? So what I'm going to do, I'm going to clear the board here. And when I clear the board, we're going to redraw the hemiacetal in order for us to continue and show you how you get to the full acetal, because that's the real goal of this reaction, is let's get to the complete acetal. All right, give ourselves enough room. Okay, we're done with this arrow. So if I bring the hemiacetal back up here, so let's go ahead and redraw that. We'll continue in blue here for now, showing that we're in the second portion of this reaction. All right. So here's the OH. Keep in mind that we regenerated our acid catalyst. So here's the OCH3. And the OH would now take a hold of the H+. Now some students have a tendency to ask me at this point, well, why wouldn't the OCH3 grab the H+? Well, that's possible, but then you've reprotonated your alcohol and the alcohol would leave instead of water. And I say that's possible because both of these are oxygens, so they could both potentially go after and grab this H+. And keep in mind, I mentioned the reversible conditions. So these arrows right here, those represent reversible conditions, meaning I could go backwards towards the ketone. And it turns out that these types of reactions can be used to protect ketones and aldehydes so that there can be subsequent reactions run and then you can deprotect them and bring them back to the ketone or aldehyde form. All right, so if I grab this, I'm going to form water. Now, alcohols themselves are not particularly good leaving groups. However, water is going to be a good leaving group because it will become neutral in solution and it will get rid of its formal charge when it's hanging out on the carbon. So if this becomes H2O, H2O is going to have a positive charge associated with it while it is on the alkyl substrate. And what's going to happen here is that we will have water leave, and where you could start forming a carbocation at this tertiary spot, it turns out that we can use a set of these lone pairs to temporarily alleviate that behavior. So in other words, we're going to avoid the carbocation formation because we have some resonance availability there. So water's gone, water has now left, and what I end up with, okay, I'm moving the alcohol that was at the bottom to the top here. I haven't rearranged any bonds, I'm just taking what's down here and moving it to the top so it's a little tidier as we get ready for our next nucleophilic attack. Okay. Whoops, I should not have that second set on there. Okay. So I now have something that looks like this. The oxygen is taking on the formal charge that the carbon would normally have here. Again, these are resonance structures, so you could have a carbocation present at the bottom. And again, this is an activated type of carbonyl. So the second alcohol will very readily come in to attack that carbonyl. So you're going to have this come in. It'll attack here. And then, again, reversible conditions. We're going to end up with an OCH3 at the top and an OCH3 that's protonated, because again the alcohol came in with that proton. It doesn't just get ditched on the way. Positive charge on this guy here. Alright, so here you go. Now the last thing we need to do is go ahead and remove this proton, give the electrons back to the oxygen, and now we have our acetyl. So you're really sort of repeating the same step when you get to this second portion, when you go from the hemiacetal to the acetyl. It's just that you now have an activated carbonyl with the methoxide group instead of with the alcohol. You do another attack, you do another removal of the acidic proton to regenerate the catalyst, and here you go. You are up here at the acetyl. All right, so that is the acetyl formation, and this reaction is referred to as an acetyl formation. The hemiacetal is a very important intermediate, so you're going to want to be able to identify or know what a hemiacetal is versus what an acetyl is. And that will work with aldehydes or ketones. Remember that all the steps are reversible, and that pretty much covers what we want to look at in terms of acetyl and hemiacetal formation. So up next on the list is going to be the imine and the enamine formation. So I will go ahead and I will bring up that reaction. Give me just a second here and then we'll go over that. Okay, there we go. So what I have right here is an imine formation. So when we're dealing with imine formation, you're going to be using a primary amine. So let's spell out some of this so we know what we're talking about. Imine, with an I, is the type of product that I have over here. This is an imine. I require a primary amine, the type of functional group. So what I'm talking about here is this NH2 should have one other carbon group on it, not more than one. That makes it primary. And then again we have our ketone that we utilize over here as a starting material, because this is the aldehyde ketone chapter. Now, when we take a look at this, all right, similar to our acetyl formation, we're going to have a protonation of the carbonyl due to these acidic conditions. Now, something that's very, very important for this reaction, and you're going to want to take note of this, is that the pH needs to be somewhere in a range of 4 to 5 for this reaction. And the reason for this, and it's more so with the imines and the enamines than with the acetyl formation, because the nitrogen is a very, very sensitive base to these acidic conditions. In comparison to alcohols, alcohols are not as basic as nitrogens are. So when you're dealing with this, if your pH gets too low, so if we have a low pH, meaning a pH of, let's say, 1, okay, that means you have highly acidic conditions. If you make the conditions too acidic, the problem is that the amine is going to come by and pick up one of the protons in solution. If it does this, that means that, the nitrogen has given away its only lone pair and now becomes an ion like this. This does not have any nucleophilic ability because there is no lone pair that's present on the nitrogen anymore. So that ruins the reaction. If your acidity is too high in this case, it's going to ruin the nucleophile. Okay? Now what happens if the acidity is too low? So if we have a high pH, right? Let's say we have a pH of something like 12. What's going to happen? Well, in this case, this is problematic because if I have a high pH of around 12, that means I have almost no acid present, and that means that the carbonyl, which needs to be activated, is not going to be able to find any hydrogens. It's going to go look for an H+, and it's not going to find a whole lot of them out in solution. So we're going to have trouble activating our carbonyl if we keep the conditions too high on the pH scale, meaning we don't have enough acid present. All right, so just very important to note why we need to keep a very narrow range for the pH here. And that's important both on the low side because we could ruin the nitrogen nucleophile, and it's important on the high side because we're not going to have any type of carbonyl activation, which is required. So pH of 4 to 5 for this reaction. This reaction, similar to the acetyl hemiacetal, in fact you're going to see a lot of similarities, is a reversible reaction. So we want to make sure we're doing double arrows when we see this. Once we protonate and we get our activated compound, we're going to have the nitrogen attack this time. So last time when we were looking at the acetyl, we had an alcohol attack, very similar. Now we have an amine, and the amine will attack this group here as we move these electrons up to the oxygen. So when I get ready to bring that in, I'm going to look at another type of proton transfer situation. So here I'm going to have the alcohol. Okay, and a lot of students will also ask me here, don't you have a hemiamine? And technically, yes, you would have a hemiamine here. However, the hemiacetal is much more relevant in certain biological reactions, and so it tends to get focused on in terms of its name, whereas we tend not to talk about hemiamines very often. So this is a positive charge associated with the nitrogen down here that gave up its only lone pair to come in and attack. And so we would have a proton transfer. Now in this case, because I'm not too focused on the hemi formation here, I am going to write H+ transfer. Okay, now what happens, and you'll see this a lot of times in organic chemistry textbooks or classes, it means that this hydrogen has left the nitrogen and has been transferred up to the OH. So we're saving ourselves a little bit of monotonous writing by simply saying, hey, look, we've taken a proton off and we've put a proton back on in the H2O position here. And that means that I have a nitrogen with a CH3 here, and it has a lone pair. All right, now if you were following along with the acetyl formation, you should hopefully realize that what's going to happen here is the water will leave, and the nitrogen is going to come and assist through resonance with what would initially be a carbocation formation here. And so what we end up with, again I'm going to swing this up, the water is gone, and the nitrogen now looks like this. Now I'm forgetting something here. This is actually we had 2 hydrogens, right, on this nitrogen, because it was NH2. So I forgot to bring one of those hydrogens in when I was writing it. So we lost one of the hydrogens in a proton transfer. The other hydrogen is still present, and that's going to be important here. We have to have a hydrogen present to get to the final product, because now we want a neutral nitrogen up here. We have to, again, similar to the acetal, get rid of one of these protons and send them back into solution. We're going to give the electrons to nitrogen, and we come up to the imine that we have here as the final compound. Okay. My apologies for that. I forgot to carry over that hydrogen as I was working with this. All right, so that is the imine formation. Again, aldehydes and ketones can undergo this type of formation. You take a look at this, you've got a double bonded nitrogen. Now there's a similar reaction known as the enamine reaction, and that's what we're going to bring up here next. Okay, so what I've brought up here is the enamine reaction. It's going to be very similar to the amine reaction, but the imine reaction had a primary amine, whereas the enamine is going to have a secondary amine, and that's what's important here. So if you take a look, we have the secondary amine, meaning I have 2 R groups or alkyl groups and only 1 hydrogen present this time. I still have my ketone. And then if I take a look right here, this is known as the enamine. And this term comes from En for double bond, like when we talk about enols or alkenes, and then amine, enamine. So similar to an enol, instead of an alcohol, this has a double bond next to an amine. And this reaction is going to be identical in its steps up until the very last section of the reaction. So you'll go through, you'll create the water will leave. So I am going to spare everybody rerunning through the imine reaction, which we just took a look at. So let's sort of cut to the chase and come down here and say, what would we be left with? Well, I'm left with this functionality right here. And in order to get the proper product, now note that the product here, or the intermediate here, has a double bond. This is more similar to an imine that I have right here. So this would be the compound I'm dealing with right before the end of the reaction. Well, because I don't have the ability to give any electrons here without creating a carbocation, I'm going to have to take my hydrogen in order to replenish the hydrogen that's catalytic up here. Remember last time in the last step we had a hydrogen left on the amine. This time we don't. We're going to have to take it from one of the slightly acidic surrounding alpha carbons, similar to enolate chemistry. So one of these hydrogens is going to be removed and give its electrons over here, and that allows an alleviation of the nitrogen charge. So we can get rid of that double bond. So what I end up with is the enamine right here. Again, a very similar reaction. However, the primary thing to consider here is the type of amine that you're working with. So maybe I shouldn't say the term primary because that'll confuse you with primary amines, but the major thing you want to consider is the type of amine you're working with. Are you working with a primary amine or a secondary amine? If you're dealing with a primary amine, you'll do imines, and if you're dealing with a secondary amine, you'll do enamines. And the mechanisms are the same up through the very last step. So that covers amines and enamines. The next thing we are going to take a look at, I'll clear the board here, is going to be the cyanohydrin addition. And once we take a look at the cyanohydrin addition, we will take a look at reductions. So give me a second and I'll bring that up. Okay, so what I have brought up here is the cyanohydrin addition. And this is, simply as the name implies, the addition of an alcohol and a cyan, or what's known as a nitrile group, which is a C triple bond N. So when we're talking about this, keep in mind that Cn is a group that looks like this. Now, the way that this works is you tend to pair this reaction with an acid-base type of equilibrium here. The base is simply going to act as a catalytic addition, and then you can use HCN in order to promote some sort of acidic formation, because this is a acidic form of the nitrile ion. And when we deal with this, you would first grab a hydrogen, and that would donate its electrons to the CN. So what we're dealing with is creating a source in solution of CN minus, like this. So once I have this, and again, reversible conditions here for this one, the next one we take a look at will not be reversible. So when I take a look at this, I've got an activated carbonyl. And this one is a bit easier than the acetyl and the hemiacetal. All we need to do is bring in the C triple bond N. And when I do that, it's going to attack the carbonyl. This will break open, and I'm there. So again, much shorter explanation when we're dealing with this. And hopefully you're seeing the repetitive formation when we deal with these acidic conditions, that we activate carbonyls, then we toss in the nucleophile, and then we end up with what we need. This particular case, the acid-base reaction that we have going here can work because we have an acidic form and a basic form that have the same conjugate forms as one another. So that's why this works. You couldn't do this, for instance, with an alcohol, because if you had the methoxide, the corresponding methanol would not really be acidic enough in order to protonate or give any sort of activation of the carbonyl. So that's why those steps are a little bit longer when you have a separate acid. You can't directly add the base without its proton. All right, so that takes care of the cyanohydrin addition, and the next one that we're going to take a look at is reduction. Now reduction, which will be followed shortly by a brief discussion of oxidation in relation to aldehydes. Oxidation reduction are complementary reactions, which means that they are opposites of one another, and they tend to go hand in hand when you're learning them. So what I have here is an example of a reduction with a ketone going from the ketone to the alcohol. So reductions provide carbonyls, and they reduce those carbonyls down into the alcohol form. So when we get ready to look at this, there are multiple reducing reagents. I have one of the most common ones up here, which is NaBH4, and then you can also use what's known as LAH. Now LAH is lithium aluminum hydride, so I'll put that up here as a note. LAH, lithium aluminum hydride. This is sodium borohydride, but notice that we're dealing with hydrogens, and hydrides specifically are dealing with the negative charged form of a hydrogen. So what I want you to focus on here is the fact that we're going to be generating H- given these reagents. That's what they're going to liberate or allow to go into solution, is H-. Kind of a rare species in comparison to some of the other nucleophiles that we see. Very, very reactive. Now, notice that these are numbered 1 and 2. And that's important because when you have numbering like that, it's stating that these steps must be taken separate from one another. So in other words, I cannot add the sodium borohydride and the acidic conditions together. I have to add sodium borohydride to my ketone first, allow it to react to completion, and then I will do a second step where I add H3O+. Very important that those are kept separate when we're dealing with that. Now, if I take a look here, the hydrogen, the hydride, is going to attack the carbonyl because it is a strong base. So now we're dealing with a base type of addition. Notice I did not do any sort of activation of the carbonyl. I simply directly took my base and moved it into the carbonyl spot. And what this provides us with in a non-reversible condition is I've added a hydrogen here, which tends to be implied, and then I have an O- that's left up here. And so once all of this ketone has reacted with the provided hydride, at that point I will do step 2, which is H3O+. And H3O+, or any appropriate source of acid that you'd like to use, is going to protonate the remaining O- here and provide water as a side product. So you will have water as a result here, and then you'll have the alcohol form. Again, there's an H here, which is typically implied because it's just part of the hydrocarbon chain at that point. But there is a hydrogen that's been added there. So if I take aldehydes and I reduce them, I end up, so we'll put an R for reduce, I end up with a primary alcohol. If I take ketones and I reduce my ketones, I end up with a secondary alcohol. Okay. Now, you can also reduce carboxylic acids, esters, things like that. Those groups require LAH. LAH is a stronger reducing agent. This tends to be, NABH4 is weaker. NABH4 will only work with aldehydes and ketones. That's important to note. NABH4 will only reduce aldehydes and ketones. Lithium aluminum hydride, LAH, will reduce anything. So you'll get aldehydes reduced, ketones reduced, carboxylic acids reduced, esters reduced, and there's a lot of other groups that can be reduced using lithium aluminum hydride. All right, but sodium borohydride, it's a milder reagent, it's safer to work with, and it works just great with aldehydes and ketones. So you will typically see NABH4 for aldehydes and ketones, and then lithium aluminum hydride, you could use it with aldehydes or ketones, but it is also reserved for the higher oxidized groups, such as carboxylic acids, esters, and hydrides, all of those sorts of groups. But we're focused on aldehydes and ketones here, so we're not going to look into all of that until we get to the proper lectures on carboxylic acids and esters. All right, so again, aldehydes will reduce to primary alcohols, ketones will reduce to secondary alcohols. The only thing you really need to know here is that you will generate H-, and that will attack the carbonyl group, which has a partial positive here, using the sodium borohydride reagent. And that is reduction. Now, oxidation is going to deal with, again, only aldehydes in the ketone aldehyde lecture series, and that's because ketones are already oxidized to the maximum extent. They cannot be oxidized further. So let's pull up a basic oxidation. We're not going to go through the mechanism of the oxidation, but we will talk about just the general idea of oxidizing an aldehyde, and then we'll take a look at enolates and aldols. Alright, so what I brought up here is a basic oxidation that you can work with. And when we do oxidations of aldehydes, they are going to be converted into carboxylic acids. So you can see here, I've used an oxidizing agent. Now I do want to mention there's other oxidizing agents. You could use Na2Cr2O7. You could use KMNO4. Okay, there's several common ones. A lot of times you may see this written over an arrow like this with an O, and that generally stands for oxidize or oxidation process. Now, when you take a look at this aldehyde here is going to be oxidized up into a carboxylic acid. And what we're talking about in terms of the oxidation is the oxidation of carbon itself. So remember that oxidation is a loss of electrons. So some people, you say Leo, Gur, like Leo the lion says Gur. Some people do oil rig. But the key here is that loss of electrons is oxidation. So we're talking about carbon losing more of its electron property in comparison to that of the aldehyde form versus the carboxylic acid form. So here, in an aldehyde form, I've got a pull on the electrons that the carbon has up towards the oxygen. The oxygen is electronegative. However, the hydrogen would be partially positive here. And we're looking at this relative to the carbon. So then if I go over to a carboxylic acid, I've got the C double bond O, which is pulling electrons in this direction, but then I also have an OH instead of just an H. And this oxygen is also partially negative. So the electron density, or if you were to look at the actual oxidation state, the oxidation numbers of this carbon, okay, the carbon is continuing to lose electrons. It's becoming more and more positive in nature as I continue this oxidation around that carbon. So what you're looking at is this, now adding an additional oxygen here, and this oxidation process is going to make a larger partial positive carbon here. It's going to change its oxidation state. It's going to become more positive and lose more electron property in this process. So again, there's several reagents you could find here. A ketone does not have the ability to undergo oxidation, which we've stated before. You're really looking at aldehydes in this process. Now I do want to mention, and we'll go over this when we talk about alcohols, but an alcohol itself can be directly oxidized up using CrO3 into this carboxylic acid. An aldehyde would be an intermediate form that you could end up with. However, the end state of this oxidation would be this here. So whether you're dealing with alcohols or aldehydes, using strong oxidizing agents is going to have a process where you take these up to a carboxylic acid when they are fully oxidized. So that's oxidation, the opposite of reduction. Keep in mind, in reduction we were adding hydrogens to the carbon. Now we're adding oxygens to the carbon. Those have opposite electronegative effects, and therefore, again, oxidation, reduction, those are complementary processes. They pair together. They're opposites of one another, but they sort of go hand in hand when you're dealing with the electron density around carbon and either increasing or decreasing it. So that's oxidation. The last thing we're going to take a look at here is an aldol reaction. And this has to deal with some of the enolate chemistry that we were looking at in the previous video. So let me clear this. I will bring up a general aldol reaction, and we will go ahead and discuss the enolate aldol reaction. So let me pull that up. Alright, so what I have pulled up here is a basic aldol condensation. And this stems from enolate chemistry. So keep in mind, when we were talking about enolates on the last lecture, we said that these alpha positions right here, that's considered an alpha position, if they have protons on them, those protons are considered mildly acidic and they can be removed in order to form enolates. And so all I need is a base in order to remove one of those acidic protons. One of the most common bases that tends to be used for aldols is sodium hydroxide. You will see several others. Methoxides and ethoxides tend to be utilized in what's known as Claisen condensations. They're somewhat similar to an aldol, but they use esters instead of aldehydes and ketones most often. And when we are dealing with the aldol condensation, we deal with hydroxides, or sometimes there's a stronger base known as LDA, and that's a type of an amine base that's negatively charged. That can also be used in place of sodium hydroxide. Now, when I'm getting ready to do this, the hydroxide itself will act as a base, and it will provide the pulling power to get rid of one of these alpha protons, and the proton that it picks off will give electrons to the carbon, and so we end up with an enolate. Now, this is also a reversible reaction when we deal with this. So the enolate form, now we showed two of them last time. You can have the double bonded oxygen with the negative charge on the carbon out here, or through resonance you can put it into its favored resonance form, which is to keep the negative on the oxygen. So you would have something that looks like this, and then you would have the ene that goes with enolate, so that's the double bond there. Now, what happens after this is that because there is some negative charge associated with this carbon right here, this carbon has the ability to go out and to attack other carbonyls. So if you have a second equivalence of acetone here, what you can end up doing is taking the enolate group, you take the acetone, the second acetone, And the enolate will act as a nucleophile, and it will come and attack this carbonyl right here. Now you're going to move these oxygens up, the electrons associated with that oxygen up, again, because carbon should not have 5 bonds at any point. And what you deal with here is you end up with what's known as an aldol condensation. So what I'm going to do is I'm going to highlight this in various colors so it's a little bit clearer here, right? So what we're going to first work with is we're going to say, okay, this portion right here is going to be associated in red. So I had a CH3, and it was back and forth with the resonance, but I have a C double bond O, like this. And then the enolate portion attacked the carbonyl of the other group. So in other words, this carbon right here is associated with this carbon right here. And that double bond is now being formed into a single bond, or you can say that these electrons are being used to form a new bond. Either or is acceptable. All right, so if I take a look here, this bond is going to be attached to, now I'm switching colors here, all right? So let's do, we were doing blue over there, let's do purple just to keep it separate, right? So the purple portion is going to be dealing with this portion that it added to. So now this added to the carbonyl, so this right here is what I'm dealing with. And this carbonyl had 2 methyl groups, so I need to make sure I end up with 2 methyl groups right here. Now that carbon has 4 bonds, so I haven't violated any sort of valence rules yet. Okay. Now if I come up here, the last portion of this reaction would need some sort of acidic workup. So sometimes you'll see this with H3O+, sometimes you'll even just see it with H2O. H2O is mildly acidic. It's acidic enough that you could end up using it to protonate this alcohol here. And this would grab the acidic proton that it needs, and you end up with your aldol. Now the term aldol comes from aldehyde and alcohol. Now again, this can be run with a ketone or an aldehyde. So the root word with the ald just comes from the fact that you can do this with aldehyde. So you could also call it a ketol if you were doing it with a ketone. But you'll typically just hear it referred to as an aldol product. And that's because the aldehyde or ketone you started with, plus the alcohol that results, is going to be your condensation product that comes out of this reaction. All right, now one of the things that I wanted to mention along with these types of aldol condensations is that you can further this reaction by dehydrating the alcohol. So let's go ahead and let's take a look at that. I'm going to pull up a fresh reaction scheme without all of this drawing on it, and we'll take a look just at the aldol product and the dehydration that would follow that. So let's clear this and get a fresh reaction up there. All right, so now that we have a clean reaction up here, let's go ahead and take a look at what would subsequently follow with the dehydration. It's not very complicated. If you use acidic conditions, and especially if you're going to add any sort of heat to those acidic conditions. So remember we said you're going to want some sort of an acidic profile in order to work this up. Now if you had water, this probably wouldn't work, but if you had H3O+ or any other source of H+, it's going to, especially with any sort of heat, you're going to have this alcohol pick up the acidic proton, and what you'll end up with is a protonated alcohol. This is especially effective because we're dealing with a tertiary alcohol right here when you're looking at this. Now it is possible this could be a secondary alcohol if we were dealing with certain aldehyde condensations. However, right now we have a tertiary alcohol, and this alcohol is now protonated after it picks up the hydrogen to become water. Well, similar to some of our other reactions like the imine and enamine and the acetal reactions, we know that water is a good leaving group. And if water is going to leave, it turns out that as water leaves, we can take this intermediate down into a carbocation like this. especially since I'd be leaving a tertiary carbocation behind. Okay. So I'm going to make that plus a little bit clearer there. So this carbon right here would have a carbocation associated with it. Now, in a dehydration is a type of elimination reaction. And specifically, if you have a carbocation, this is an E1. Okay? So E1s would occur with 2 steps. So you're dealing with the removal of the group, and then once you have the carbocation, you're dealing with the elimination of a proton. So what you would need at this point, after you go ahead and you do this acidic dehydration, you would have a water molecule, which you just released, so you have water present, that would come, it would grab one of these hydrogens, and the electrons from that hydrogen could go to form a double bond here. So the final result, what we would have, is a compound that looks like this, because you have eliminated the alcohol from that site in order to give an alkene product. And what's important here is if you see that there's a double bond, a single bond, and then a double bond right here. This is referred to as a conjugated system, and conjugation is very favorable. It has to do with the fact that you have p orbitals overlapping at each of these sites with one another. So conjugated products are highly favored. So this is not a very difficult reaction to drive forward. After I have my aldol product, I can further dehydrate it with little to no effort. All I need is a little bit of acid and a gentle heating, and I can easily dehydrate this and take it over into the conjugated, basically it's a beta keto unsaturated group that you have here. The beta referring to this position where the double bond is. So you'd have a beta keto that you're dealing with. So that deals with the aldol condensation. You want to understand the aldol reaction and the fact that these products can undergo a dehydration afterwards. So hopefully you found all of this useful in explaining reactions. And what we will do is we will bring up a series of questions, as we usually do, to test you guys on some of the material that we went over here. I just want to mention briefly here, if you find yourself doing well with these questions, and then you go and you utilize some of the actual questions that come along with the program, so the bank questions, and you find that they're much more difficult, we've designed it this way on purpose. So the idea is we want to give you some of the most difficult, challenging questions that you can find in that question bank, so that it's sort of like you're training for a marathon with weighted clothing, so that once the actual marathon comes, the marathon being that you're training for the MCAT, you're able to just full out sprint and nothing's affecting you at that point. So keep that in mind. If you're struggling with some of the questions that we have in the question bank, and then you're saying, well, the ones on the videos seem a little bit easier. These videos are designed for guidance in terms of delivering the basic information to you. The questions that we actually put in the bank are going to be some of the more challenging questions in order to really amp you up and prepare you for the real thing. So keep that in mind. If you see any discrepancy or you seem discouraged, keep going forward. Don't stop. You're in the middle of your training and you're getting ready for the actual event, the MCAT that you're going to be taking. So I just wanted to take a side note and mention that, especially in a lecture like this where some of the material is very heavy in terms of organic chemistry and synthesis, because I know that that can be overwhelming at times. So let me clear the board here now that I've said that. I'll bring up some of these practice questions, and then as usual at the end we'll go ahead and we'll bring up our summary table, especially for these reactions, because we have different conditions and what's reversible, what's not. We'll do a nice summary at the end. So let me clear this off and bring my questions up, and we'll get started from there. All right, everybody. So now I have the questions up here, so we're going to take a look at these. So the first question says, the following reaction is best described as, and you have several options here, A, B, C, and D. Notice that they all mention aldol, so it should be evident to you that this is an aldol condensation. You're going to be providing some more specific information on the aldol reaction. Okay. And then number 2 says the compound shown below is, and you have several options A through D. So these are the two first questions. There will be another set that I put up after this, but go ahead and pause the video. Try to work through these by yourself and see if you can understand the reasoning behind your answers before going through the guided solution. So again, the following reaction is best described as, it's going to be an aldol of some sort, and you'll get the answer. And then number 2, the compound shown below is. So we're classifying this compound based on the options there. So go ahead, try these, and pause the video, and then we will go over them in a minute. All right, so for question number 1, the following reaction is best described as. So option A, B, C, and D all deal with aldol condensations. A talks about a thermodynamic controlled aldol condensation. B talks about an aldol condensation using acetone as the starting material. C talks about a kinetic controlled aldol condensation. And D talks about an aldol condensation with a subsequent dehydration. So hopefully the one that was easiest to pick off out of this grouping here would be the one that is option D. And that's because there is no subsequent dehydration. The alcohol is still present in the product. And if that's the case, no dehydration occurred, so D would be out. The second easiest one to identify would be that B should be removed. And that's because we're using 2-butanone as the compound for the starting material, not acetone. Acetone was used in the lecture examples, but it is not being used in this particular problem that we have here. So that leaves us a question of a thermodynamic controlled aldol condensation or a kinetic controlled aldol condensation. So what you need to do is take a look at the connecting portion. So your enolate is going to be this group right here. This is your enolate. And you know that because it connects to the corresponding carbonyl group that then opened up and became an alcohol. So if I take a look at what I have circled over here in terms of the enolate, and then I take a look at it over here, the structures are very similar. It means that the enolate was formed at this position right here. And this particular position is going to be the thermodynamic position because it is more hindered, whereas this alpha carbon would be the kinetic position. It's going to be less hindered. So we clearly made a thermodynamic enolate, leading to option A as the best answer. So again, all of these dealt with an aldol. The question was a little more specific about the type of aldol going on, and even more specific, the type of enolate that was being formed for this aldol reaction. All right, now, number 2, the compound shown below is, so we're classifying this compound. Now, if I take a look, I've got an alcohol and I have an ether. Now, when I have an alcohol and an ether along the carbon chain, this is a hemiacetal, not a full acetal. So that means I can immediately get rid of A and C. So even though this is an intermediate form as part of the acetyl reaction, a full acetal would have the OCH2CH3 group twice. It would have it above and below. So we're in the hemi form right now. Now the question here says, is this a hemiacetal formed from ethanol and a ketone, or a hemiacetal formed from ethanol and an aldehyde? That's the question. And the correct answer is B. This is going to be coming from a ketone, not an aldehyde. And that is because if you take a look at what this started from, the material that we would have started from would be 2-pentanone. And if this was an H, meaning that this right here was an H, or it might have just been implied, so you may have not seen a bond here at all, and the H was implied there, then we would be talking about from an aldehyde, because this starting material would be an aldehyde and not a ketone. So the best answer here was B. Now note that all of these state coming from ethanol. That's because this group right here was added using ethanol as the nucleophile. So that is the guided solution for problems 1 and 2. What I'm going to do is clear the board here again, and I'm going to bring up 3 additional questions to quiz you guys on this content, and then we will get into our wrap-up and summary table. So let me clear the board and I will bring up the new questions. Okay, so here is the new set of questions. Number 3, why is it important to avoid low pH levels during imine formation? And that's something that we discussed. I specifically told you should take note of that because it's a very important side detail to imine and enamine reactions. Number 4, acetone was used as a solvent in a reaction requiring strong basic conditions. Which of the following is most likely? And then there's several options there. Finally, number 5 is going to deal with hybridization of carbons when they go through a specific reaction. A reduction of a carbonyl group to an alcohol group can best be classified as, and you have several options there. So go ahead and practice these questions. We will go through the guided solution in just a minute. For right now, pause the video, go through these, and see if you can come up with the answers on your own. And then we will go over the guided solution. So I'll see everybody in just a second. Okay, so if we're taking a look here, number 3, why is it important to avoid low pH levels during imine formation? So if you consider this question, low pH levels means that it's a highly acidic environment. So if my environment is highly acidic, it means there's going to be a lot of H+ sitting around in solution, very acidic. So let's say that the pH is around 1. So let's look at the options here. The carbonyl cannot be activated. Well, the opposite of that's going to be true, because if we have a lot of the hydrogen ions around, that means that there's plenty of them for this carbonyl to pick up, and then we can get the carbonyl into an activated state. So that's a poor choice. This will ruin the electrophilic nature of the carbonyl. Well, that's not true either, because if I have the H+ here, it's going to activate the carbonyl, and that's going to make it more electrophilic, not less electrophilic. So it's not going to ruin the electrophilic nature of the carbonyl. The starting amine will attack the carbonyl too fast. Again, that's not the case here. You're not going to attack it too fast in acidic conditions. D is the best choice. The amine will no longer be nucleophilic, because if I have some amine here that's going to be nitrogen based, and I have highly acidic conditions, these conditions are going to come into play when the amine is present. It's going to pick up one of these protons and it's going to lose its lone pair, therefore it will no longer be a decent nucleophile. So the correct answer here is D. We're looking at the amine is no longer going to be nucleophilic. So for number 4, acetone was used as a solvent in a reaction requiring strong basic conditions. Which of the following is most likely? The acetone will undergo an acetyl formation. It will undergo an enamine formation. The acetone will be oxidized to a carboxylic acid, or the acetone will undergo an aldol condensation. So there's a couple of things you want to keep in mind here. Number 1, acetone is a ketone. It's the one that we were using throughout most of the examples. And number 2, we're talking about strong basic conditions. Those should be very important when you're examining this. So we can easily cross out C, because if I'm working with a ketone, ketones cannot be oxidized. That's something that we discussed. Aldehydes can be oxidized up to carboxylic acids, but not ketones. So that option is out. Now, if I look at option A, the acetone will undergo an acetyl formation. Acetyl formation is going to require acidic conditions with an alcohol of some sort. So we could use methanol as the simplest example. If I have acidic conditions, that's not going to sort of coincide with strong basic conditions. So that doesn't make a whole lot of sense. And included with that is the enamine formation also requires similar conditions. They need to be acidic, and I would need to use some sort of a secondary amine. So in that case, I'm still looking at something that's acidic in the conditions, and therefore that would no longer be a good option. So the correct answer here would be D. The acetone would likely undergo an aldol condensation. So a side reaction you have to be careful about is if you use acetone as a solvent and then you choose to bring in a strong base like hydroxide or something else, you could potentially start having aldol condensations that are occurring instead of the desired reaction. Okay? And number 5, we have a reduction of a carbonyl group to an alcohol group, which can best be classified as. So think about a carbonyl group. So I have, let's say, a ketone, R, C double bond O, R, going to R, C, H, O, H, R. Right? So if I take a look at this, now keep in mind that this H, we can explicitly draw this out here as another bond. All right? The carbonyl group right here is trigonal planar and sp2 in its hybridization, whereas the alcohol is tetrahedral, it is sp3 in its hybridization. So this was not meant to be a horribly difficult question, but you do have to understand the hybridization and the center of hybridization that's being changed when you go through the carbonyl here. So the best option is that we're going from sp2 to sp3, and that means that we are going to be changing sp2 to sp3. That's option B. So a little bit of hybridization question mixed in with an aldehyde ketone reaction. You have to understand what the reaction actually does, and then you can take a look at the hybridization that's changing there. So those are the questions that we are going to be practicing for the aldehyde ketone part 2 when we're doing this series. So I will go ahead and clear this, and I will bring up the summary table in just a moment. All right, everybody. So here is the summary for this portion of the aldehyde and ketone lecture. And I brought all of this up so that it's neat and organized in a table form. Keep in mind, if you have any questions about specific arrow pushing or reactions or things like that, you can go back and review certain parts of the video. But this is a nice summary table to keep certain points in mind. So I have this broken down by reaction on the left, the name of the reaction, the reagents and conditions we would be looking at on the right, and then I have important notes that we want to keep in mind. So let's take a look here. To start with, we discussed or talked about the acetal/hemiacetal reaction. This required acidic conditions and an alcohol of choice. You can pick out the alcohol you want. Keep in mind, the more sterically hindered your reagents, the less likely the reaction will go, or at least the slower it will go. Now, important notes. This is going to create an acidically activated carbonyl. The hemiacetal form involves one ether portionality and one alcohol, so it is a halfway point of the official acetyl reaction. And then the acetyl is a double ether reaction. Let's also keep in mind that this is reversible. Okay? Imine and enamine formation are going to use acidic conditions with a given amine. Now the amine you pick is going to matter here. This is a pH sensitive reaction. Specifically, we want a pH somewhere in the range of 4 to 5, and that means that we have a nice controlled environment in terms of having enough proton acidity to activate the carbonyl, but not so much that we ruin the nitrogen, which tends to be highly nucleophilic and basic. So it could have a side reaction if it was to be too acidic. Now, acidically activated carbonyl complexes will take the first step in the mechanism here. The imine is going to result when you have a primary amine that you are using as your reagent. And then your secondary amines will end up giving you the enamine product. So remember that the imine involves a nitrogen directly double bonded to the carbon that was the carbonyl, and the enamine reaction will have a regular amine and it will have a double bond between two carbon groups right next to that amine, similar to an enol or an enolate. Now, the cyanohydrin addition was a little bit simpler. It was base catalyzed with something like the sodium nitrile, and you can use HCN and CN- to create this sort of acid-base reagent equilibrium, and this will help to promote a quick reaction. you're going to end up with an alcohol and a cyano group that have been added to the carbonyl. This would be an sp2 to sp3 type of situation, similar to the reduction. So reductions are going to use sodium borohydride followed by acid. You could also use lithium aluminum hydride, which we talked about. Carbonyls are going to be converted into alcohols, and in this particular lecture we looked at aldehydes and ketones being turned into this set of alcohols. However, we did also mention that esters, carboxylic acids, and some of the derivatives of carboxylic acids can also be turned into alcohols. Now, the NaBH4, the sodium borohydride, is a weaker reagent, so it can reduce aldehydes and ketones just fine. However, you are not going to be able to reduce some of the other ones we just mentioned. The LAH, the lithium aluminum hydride, is a much stronger reducing agent, and it can still be used for aldehydes and ketones. However, it tends to be reserved for some of the more highly oxidized species, such as carboxylic acids and esters. Aldehydes are going to give primary alcohols when you reduce them. Ketones are going to give secondary alcohols when you reduce them. Okay, then we talked about oxidation, which is sort of the complementary or opposite reaction of the reduction. The example I gave used CrO3. However, there are lots of other reagents that you can use besides the chromium trioxide. You can use KMNO4 or anything that heavily uses your oxidative power, which usually is represented by a number of oxygens at the end of the reagent. A common way of stating this is just O in brackets, and that stands for take your pick of any strong oxidizing agent and oxidize. This is run with acid. It does not have to be separate like the reduction does. Remember, see how it says NaBH4 followed by acid. Those steps have to be separate. Whereas the oxidation, you can have acidic conditions, and you want acidic conditions while you have the oxidizing agent present. So this is only available for aldehydes. This is not available for ketones. We cannot oxidize ketones up to any higher oxidation state. Only aldehydes can be oxidized up to carboxylic acids. And the carboxylic acid is a result of an aldehyde oxidation. You are going to be increasing the oxidation, or what you would call the oxidation number, the oxidation state, of the carbonyl carbon. So the hydride is reducing that value, whereas the oxidation is increasing or making that value greater, meaning it's losing more electron density. Remember, loss of electrons is oxidation. And then finally we have the aldol condensation. The aldol condensation requires a strong base, and that can be followed up with a mild acid. It does not have to be a very strong acid. You can, however, use a strong acid, and if heat is present, you will very often dehydrate. So keep in mind that when you use your strong base, you're going to promote enolate formation, and these enolates will attack another carbonyl compound. This will form a carbonyl and alcohol-based product, and that's where you get the term aldol, aldehyde alcohol. And these are easy to dehydrate because you're looking at the conjugation. So it's easy to dehydrate because you're going to be promoting a conjugated system which contains high stability. So they are very easily dehydrated through an E1 type mechanism in order to give the alkene that is conjugated to the carbonyl. So that wraps up and brings us to a full summary of the aldehyde-ketone reactions, and it covers the rest of what we needed to touch base on in terms of aldehyde and ketone chemistry. So hopefully this video was useful, and it helps you gather a little more understanding in terms of aldehydes and ketones and what you might expect to appear on the MCAT, and we will see you guys for subsequent lectures. Thanks a lot.